This concluding episode will be about electric and magnetic fields in special relativity. But maybe it should have been the first episode because, historically, Albert Einstein began his quest for a different understanding of space and time because he had asked himself as a 16-year-old the following question: in which inertial frame should Faraday's law, Ampere's law, and Gauss's law hold? After all inertial frames ought to be the same. Now, this is the question which ultimately led him to develop the special theory of relativity. But first, we have to study some basic electromagnetism. You know, of course, that there are positive charges and negative charges in nature, and unlike charges attract each other, whereas similar charges repel each other or push each other apart. But the question is, why does a positive or a negative charge feel a force? That's because any charge that's placed in an electric field, E, experiences a force, which we'll call F, that's equal to the size of the charge, let's call that small e, times the electric field. So, the bigger the electric field, the bigger will be the force. And the more charge that I put on this over here, the bigger will be the force. In fact, this is the only way that we have for knowing whether an electric field is present. If you put a charge in an electric field, only then will it feel a force. Now, if we decrease the size of the electric field and change its direction, then of course the force that will act upon this charge will be in this direction, and it is roughly half the size of the force that acts upon this charge here. Now, E is an example of what we call a vector field. More generally, if we have a vector that's situated at each point in space, then that makes up a field of vectors. So suppose that at this point in space, I have a vector that's this long and points in this direction, and at this point, it's this long and points in this direction. And similarly, if at every point that there is in space, and of course there are an infinite number of points, then if I know what the length of the vector is and its direction, then I say that I know what that vector field is. A charge, of course, feels a force in the electric field, but it's also the source of the electric field itself. So if I have a positive charge, it's the source of an electric field that's radially outwards. So the lines of electric force, or the lines of the electric field, are pointing radially outwards. The strength and direction of that electric field are got from this formula, which says that the electric field decreases as the square of the distance away from the center, and it's in the radial direction. So this unit vector r points radially outwards like this, and it has length 1. With a negative charge, the only difference is that the lines of electric force are now coming into the charge. And so you could say that the negative charge is a sink of the electric field, whereas the positive charge is a source. So, what if you have both of them together? You can see that the positive charge is a source, whereas the negative charge is a sink. And so, here is the electric field at each point in space got by adding together the vectors, the electric field due to the positive charge and the negative charge. Now, the force between the two charges is got from here. It's the charge of the first times the charge of the second divided by the square of the distance between them, and it's in the direction that connects the two charges. So the unit vector r is in this direction, going from the positive to the negative charge. You can easily see that the positive charge is being attracted towards the negative one, and so r is in this direction. Now, this formula comes from this formula. So it's the positive charge situated in the field of the negative charge, which is E minus in the r hat direction divided by the square of the distance between them. So E over here is E plus, and this E is the electric field generated by this charge. Now, in some books, you might have seen that this formula is written somewhat differently. It's written as E over 4 pi epsilon naught r squared, unit vector r. And so instead of 1, I have 4 pi epsilon naught. Epsilon naught is just a constant whose value you can look up in a book. Now, that's just a different system of units, and both of them are used widely in physics, but I will prefer this, and this is what we will use in this course. This is called the CGS system of units, and this is the MKS. Now, of course, if I have 4 pi epsilon naught here, then I would have 4 pi epsilon naught here as well. Now, if I have lots of charges, I can create an electric field which is very uniform. So, for example, here I have positive charges and negative charges here. The electric field will point in this direction, and there's so many of them that there's almost a uniform field here. And I'll still get a uniform field when I rotate to this position or to this position. So this is a situation that you would experience if you had two parallel metal plates like this, what we call a capacitor, and there are positive charges here and negative charges here. So in between, the electric field would be almost uniform, and it'll be pointing in the upwards direction. Now, what if I have a positive charge situated in an electric field and it is now free to move? So, it will move along the electric field, and it will move according to Newton's law of motion, which says that the mass into the acceleration is equal to the force. But of course, these are vectors, so mass into acceleration vector is equal to the vector force. And so you could write this somewhat differently. You could write this as m d2r by dt squared is equal to E times the electric field vector. Now from here you can see that you cannot have lines of electric force cross each other like this, because let's say that the particle had reached this point. Well, should it go in this direction or this direction? It cannot go in both of them. And so an important point to remember is that the lines of electric force never cross each other. Well, what if there was a negative charge instead? No surprises here. It would simply go in the other direction. So it would go in the direction opposite to the electric field. Let me now talk briefly about magnetic fields. This is going to be similar in several ways, but with one very important difference. There is no such thing as a magnetic charge. In nature, there are plenty of electric charges, but a magnetic charge has yet to be found. You are, of course, familiar with the attraction between two magnets, when they're placed in this way. So this North Pole attracts this South Pole and vice versa. On the other hand, if you have a South Pole and a South Pole, or a North Pole and a North Pole, they will repel each other. Here's how you probably learnt about magnetism in the first place. There's a magnetized piece of iron, a permanent magnet, and if you spread iron filings around it, then those filings take this kind of shape. It looks very familiar. It's almost as if there were two charges, a positive charge and a negative charge, and a field between them. Here's another picture. Now, some people think of this as a North Pole, as a kind of a positive charge, and this as a kind of negative charge, and so it helps us imagine what a magnetic field is. But, as I said, there is no such thing as a positive magnetic charge and a negative magnetic charge. Still, we can think of these lines as being lines of magnetic force. But what do these lines of magnetic force actually do? What is the effect that they have on something? Here's an answer. Suppose you were to take a compass. Now, just to remind you, a compass is, you can think of it as a bar magnet. So, it's like this, a north and a south pole with magnetic lines of force around it, just as you saw earlier. Now, this can rotate around. So if there's a line of magnetic force, this red line over here, B, and if you were to put a compass, then that compass needle would be pointing along the direction of that magnetic field line. And so it follows it around as you go along it. In fact, here's a rather nice picture. You see that there are lots and lots of compasses and a bar magnet that has been placed over them. And you can see that the North Pole over here, so let's call this the North Pole and this the South Pole. Well, the South Pole of this magnet in the compass is attracted by the North Pole, and the North Pole of this compass over here is attracted by the South Pole over here. So it's almost as though there was a positive charge here and a negative charge here, positive here, negative here, and so forth. What if you moved an electric charge along a line of magnetic force? So here's an electric charge that's moved along this line of magnetic force, and it feels no force. But if this electric charge was to move perpendicular in this direction to the lines of magnetic force, so either this way or into the paper or the screen or out of it, you would have a force acting upon that charge. So here's another picture. Here is the electric charge moving with velocity v in this direction. Here's the magnetic field, and the force that would act on a positive electric charge would be in this direction, so out of the paper. And the force, this is by the way called the Lorentz force, depends upon how strong the magnetic field is, how fast the charge is moving, and upon how much charge there is. So the faster the charge moves, the bigger the magnetic field, and the bigger the amount of charge, correspondingly the force will be greater. There's a convenient way to remember this. So if you take your left hand, here's the magnetic field, here is the direction in which the charge moves. A moving charge is the same as current, and this will be the force that will act upon the charge. Well, what if there's both an electric field and a magnetic field? So, in that case, when both E and B are present, the force then is simply the sum of the two. And remember that this is the vector sum, because we are adding a vector quantity to another vector quantity. Let's suppose that there is no electric field, but there is a magnetic field that goes into the paper. And there is an electric charge that is kicked into motion towards the left. Well, it'll feel a force that bends it, and it will come back to its original position. And of course, it'll keep going around and around. I've just stopped it over here so that things can be made clearer. Here is the direction of the magnetic field. Now, it was moving down like this, so the velocity is downwards, which means that this formula, according to the left-hand rule that we just discussed, will result here in a force that is towards the center. It will also be directed towards the center when it is here. And so it will keep moving around with constant speed, changing velocity, but constant speed. We saw earlier that a single charge is the source of an electric field. But what produces a magnetic field? There are no free magnetic charges. Well, the answer is, before you, that it is the current which produces a magnetic field. And a current is the movement of charges. So, suppose there's a current that goes in this direction. Well, there'll be a magnetic field going around like this. So these are the magnetic lines of force. Same thing over here. Now this just shows a plane that is perpendicular to this wire. The magnetic lines of force lie in that plane. Of course, it doesn't have to be just a plain straight wire. Instead, you can bend it around. And if you push current through this wire, then you're going to get a magnetic field that looks like this. So it's as though you've created a bar magnet with lines of magnetic force going this way and then coming back. It's very important to note that all lines of magnetic force are closed. So this comes back and all these lines over here will come back. Similarly over here, these lines of magnetic force are closed. You could have several loops, and this will, of course, produce a stronger magnetic field. Furthermore, its shape will be different. So inside this solenoid, this coil of wire, the lines of magnetic force are almost parallel to each other and of almost equal strength. So that's one way of producing a constant magnetic field. Again, note that these lines of magnetic force, here or here, are all closed. In order to discuss the magnetic field which is produced by a long wire like this, which we're going to need very shortly, I'm going to talk a little bit more about current and current density. So, suppose that of this wire over here, I look at a little piece. I've blown it up. It has an area of cross-section that is A. It's got charges inside that are moving towards the right. And there's a total current I that flows in this wire. Let's call N the number of charges per unit volume. So there are all these charges over here, and so there's an average number of charges per unit volume of this wire. So N would be what we would call the number density, the number of charges per unit volume. If we wanted the charge density, then we would multiply N with the charge of each one of these particles inside this little volume. Now, in a wire, these charges will generally be moving upwards and downwards and sideways, but on the average, they will be moving towards the right. And let's call the average velocity of charges as v. So v is the average velocity in this direction along the wire. So let's now calculate the current that is flowing in this section of the wire. That's the charge density, which is E times N, multiplied by the volume of this little piece of wire. That volume is the area of cross-section times this distance, v delta t. In time delta t, all the charge that is within this volume over here has moved v delta t in that time. Therefore, the amount of charge contained in here is the charge density E times N multiplied by the volume, which is AV delta T, and then we have to divide by the time that it took for all this charge to cross this face of the wire. So that's delta T. Delta T cancels out, and we get the charge times the number of charges per unit volume times the speed times the area. We now define a very useful quantity called the current density. The current density is defined here. It's the current divided by this area of cross-section. So it's the current per unit area. And of course, that's trivial to calculate because that's just E times NV. E times N is the charge density, and so here's an important result, that the current density is the charge density multiplied by the velocity of those charges. Well, we have to be a little more precise because this velocity has to be in a certain direction. And so the final result is that the current density vector is the charge density scalar, this is just a number, times the velocity vector. We'll now look to see how the charge density and the current as measured in one inertial frame looks in another inertial frame that is moving with respect to the first. So let's take this frame S, in which there's an observer and a long wire which has got charges, positive charges, and these charges are at rest with respect to this observer. Now, according to S, that is this observer, the wire has got cross-sectional area A, it's got length delta x, and hence a volume A times delta x. Now the charge density, rho, is defined as the charge contained within this volume divided by that volume. And so, if the number density is n and the charge on each particle is E, then n into A delta x would be the number of charges, and then when you multiply by E, that will give you the total charge. If you divide by the volume, which is A times delta x, then you get En. On the other hand, the current is zero because these charges are fixed. And of course, if the current is zero, then the current density is zero as well. But now, imagine that this same wire is looked at by this observer. So that observer in the frame S prime looks at this wire, and there are two important differences. First, according to the moving observer, this length has shrunk. It's now become delta x prime, and that's the Lorentz contraction. Therefore, The charge density as observed in S prime will be, of course, the same charge as earlier. So, however much charge there is in here is also present over here. That has not changed. And so that is rho into A delta x. But you now divide by the volume, which is A times delta x prime. The volume of this little piece of wire has decreased. And so, if we remember the Lorentz contraction formula, which says delta x prime is delta x divided by gamma, then obviously from here we get rho prime is equal to gamma rho. Now let's look at the current density that is observed in S prime. There will be a current that's observed by S prime because to him these charges are moving in the negative backward direction. There will be an amount of charge in here, which will be the charge density as observed in S prime multiplied by the volume observed in S prime, which is A times delta x prime. So this volume here. And we divide by the time it takes for all this charge to move a distance delta x prime. And so, since delta x prime divided by delta t prime is minus v, v is the speed with which it is moving in this direction, therefore what we have is minus rho prime v, and that's just minus gamma rho into v. Now I can write this v as v over c into c. That's just to make things a little bit nicer. We could have just stopped over here because that's the important result, but there's no harm in writing this as minus gamma rho c into beta. Beta is what we've used time and time again. It's v over c. So the two new things that we've discovered are that the moving observer sees an increased charge density, and he also sees a current in the minus x direction that's equal to this. Okay, so here are the main results that we have. Rho goes into rho prime, which is gamma times rho, and jx, which was 0, goes into jx prime, which is minus gamma beta c rho. But there is a current here, and it's going in the backward direction. Now let's write these two equations in a matrix form. So remember that jx is 0. Well, I'm going to have c rho prime is equal to gamma into c rho. That's exactly this, except that I've multiplied by c here and c here. Why I've done that, you'll see in just a moment. Similarly, jx prime is equal to minus gamma beta into c rho, which is this equation. Now, instead of writing c rho all the time and jx all the time, I'm going to write c rho as j0 and jx as j1. So 1 with the index raised. Similarly, I'll write j prime 0 as c rho prime. So just the same as this, except that there's a prime to indicate that this is in the S prime frame. And this matrix should be so familiar to you by now. Isn't this just like the usual Lorentz transformation of space-time coordinates, where you transform x0, which is ct, and x1, which is x, to ct prime and x prime? Now, if you were to go to 4 dimensions, this would be quite trivial. All you need to do is add in the y and the z dimensions. So, jy is j2, jz is j3, and of course, as earlier, jx is j1, and J0 is C rho. So the point is that we've now got the components of a 4 vector. And that 4 vector has obviously these 4 components, with the 0th component being C times rho. Now, this makes the dimensions of all these quantities the same. This is rho times a velocity, so is this rho times a velocity, and so forth. Now, this is a 4 vector that will transform exactly in the same way as x transforms to x prime. So, if we have our usual contravariant position 4 vector, so this is x, y, z, and this is ct, then the coordinates in the s prime frame of an event will be got from this Lorentz transformation. And remember that we're using the Einstein summation convention so that there is a sum over these repeated indices, nu in this case. The contravariant current vector will then transform in exactly the same way. So, knowing the components of the current 4 vector in the S frame, we can get to the components of the contravariant current 4 vector in the S prime frame using that same Lorentz transformation as we use for transforming the position 4 vectors. We're now going to calculate the electric field that's produced by a long charged wire. And for this, we're going to use Gauss's law. Gauss's law states the following: the total electric flux out of a closed surface is 4 pi times the total charge that's enclosed by that surface. Now we have to understand all the words in this. First of all, if this is a wire, a long infinite wire, then we can construct a surface around this. And this is called a Gaussian surface. It's an imaginary surface that surrounds this wire. Let's take a little patch on this surface. So the area of this is dA. And obviously, if I draw a line from the wire up till this, well, this area is perpendicular to that wire. The electric flux is this area, so the size of this area multiplied by the electric field, which is in this direction, that is to say, in the direction dA. Now here what we are saying is that this little piece of area actually has a direction. That direction is normal to the surface. So the small amount of electric flux will be just dA times E perpendicular. Now for this cylinder, obviously the electric field in this direction or in the opposite direction or in the side directions will be the same. And so therefore, all we need to do is multiply by the area of this cylinder, that is to say this part of the cylinder, not the end caps. That will be this length L times 2 pi r. 2 pi r is the circumference of this cylinder. So, if you were to cut open this cylinder and lay it out flat, clearly that area would be 2 pi r into L. And so therefore the flux is 2 pi r L into E perpendicular. Suppose that this wire has got charge per unit length that we can call lambda. In that case, the charge enclosed by the surface will be just that lambda multiplied by the length of the wire that we're considering, and that length is L. According to Gauss's law, the two are the same, and so therefore 2 pi r L E perpendicular is equal to 4 pi, so that's this 4 pi over here into lambda L, which means that E perpendicular is then 2 lambda divided by r, and this is entirely in the perpendicular direction. There is no electric field that is parallel to the wire. That E parallel is 0 is of course very clear from looking at the symmetry over here, because each charge is putting out an electric field line that goes up and down, but whatever is put out on the sides, this way or that way, gets cancelled out by the neighboring charge. Now, what will be the electric charge seen in S prime? That is to say, the moving frame. In that case, the only difference is that a portion of this line will appear shortened, and therefore the charge density will be greater by amount gamma. So the gamma of the Lorentz contraction causes the charge per unit length to appear greater in the S prime frame. Therefore, the perpendicular electric field as seen in S prime will be greater by amount gamma as well. So it will be gamma into 2 lambda over r as compared to simply 2 lambda over r as observed in S. Now, of course, you could have asked, is Gauss's law, written down over here, true in S prime as well as S? And the answer is yes. That's because of the second postulate of relativity, that all the laws of physics have exactly the same form in every inertial frame. We're now going to calculate the magnetic field that's produced by this long wire through which a current is flowing. Now, for this we shall need Ampere's law. That law says that for any closed loop path, so any path that looks like this, which is closed, it doesn't have to be a circle, it can be any shape, the sum of the length elements times the magnetic field in the direction of the length element is equal to 4 pi over c times the electric current enclosed inside the loop. All right, all this calls for explanation. First of all, here is a length element, a small piece of the wire. Now, along this length element, there will be a magnetic field, so we take the product of this magnetic field times the length, which is parallel to it, and if we sum over the entire closed loop, that should give us 4 pi over c times the current that's enclosed within the loop. Let me draw a nicer diagram over here. So here is the length element, let's call that delta L, and there is a magnetic field that is parallel to this. So actually what we've done is we've taken one of these magnetic lines that loops around as our loop, and so what we need is then delta L times B parallel summed over all these little pieces, and that of course is just the circumference 2 pi r times B parallel. So we've got one part of Ampere's law, that is the sum of the length elements times the magnetic field. Okay, now the total current that is enclosed by this loop is of course just the current I. And so the enclosed current is I, and so Ampere's law says that this has to equal the enclosed current I multiplied by this factor 4 pi over c. So 2 pi r B parallel is equal to 4 pi over c times I. And so clearly from here, B parallel is 2I over CR, and there is no perpendicular magnetic field. In other words, there's nothing that's coming out like this. So on this diagram, there would be no magnetic field perpendicular to the wire. All of it would be going around in circles around this wire. Just one small remark. We have 4 pi over c, but in the MKS system of units, you wouldn't have this. You would have another constant. We're now going to come to the most important part of this lecture. If you know the electric and magnetic fields in one inertial frame, what are those electric and magnetic fields in another inertial frame that is moving with respect to the first? So, let's take this wire in which the charges are at rest with respect to this observer. This is the radial direction r, and according to S, the electric field in the radial direction, E perpendicular, is the charge per unit length as seen in the frame S divided by 2 times r. There is no parallel electric field and no magnetic field, either perpendicular or parallel to the wire. But now, let's look at this from the point of view of an observer who is moving with respect to S. As observed in S prime, this charge density has increased because of the Lorentz contraction. And so lambda has gone into gamma lambda. Of course, r doesn't change because this is a perpendicular distance. And so the perpendicular electric field as observed in S prime is then just gamma times lambda over 2r. So a greater electric field. There will, of course, be no parallel electric field for the same reason as earlier. There will be no perpendicular magnetic field, so nothing coming out like this or like this, but there will be a parallel magnetic field. How much is it? Let's calculate that by Ampere's law. So Ampere's law says that B parallel is 2 times the current divided by C times the distance r. But of course, here we need the current as is seen in S prime. And so, let's calculate I prime. That's easily done because the current is just the charge density into the velocity. The charge density, rho prime, is gamma times lambda. It's increased because of the Lorentz contraction. And so you've got more charge per unit length. Then these charges are moving backwards in this direction, so in the negative direction with speed minus v, and therefore this is the current as seen in S prime. Therefore, we've got the parallel magnetic field as seen in S prime is just minus gamma lambda v over 2cr. That's as simple as it could be. We've straightforwardly applied Ampere's law to get this important result. Now, just one last thing, and this is actually very interesting, that suppose you were to take this difference between E dot E minus B dot B, or E squared minus B squared. Well, E squared is the sum of the parallel squared and the perpendicular squared components of the electric field. And similarly, for the magnetic field, that's equal to this. Okay, so let's put in E parallel squared. Well, E parallel is 0. E perpendicular squared is lambda squared over 4r squared. So that comes here. There's no magnetic field, parallel or perpendicular. So this is 0 and this is 0. And therefore, E squared minus B squared is equal to this. Okay, now let's calculate E prime squared minus B prime squared. So this difference as calculated in the S prime frame, and that's E parallel prime squared plus E perpendicular prime squared, and the same for the B's. For E parallel prime squared, that's again 0, but E perpendicular prime squared, that, as you can see from here, will be gamma squared lambda squared over 4r squared. So that's this. And then the parallel B will give you gamma squared lambda squared v squared over 4r squared c squared. That comes from this result that we got over here. When you square this, you're obviously going to get this. So we have this difference of two quantities. Let's take the quantities that are in common. So that's gamma squared lambda squared over 4r squared. And inside, you will get 1 minus v squared over c squared. So just 1 from here and v squared over c squared from here. But you remember that gamma squared is 1 over this quantity. And so therefore their product is equal to 1. We get therefore lambda squared over 4r squared, which is exactly the same as this. So in spite of the fact that the electric and the magnetic fields in one frame and in the other frame are different from each other, nevertheless, this quantity never changes as you go from one frame to another frame. These 8 lectures have put you in a position where we've got all the necessary concepts for a fully relativistic theory of electromagnetism. That is, the equations of Maxwell, which include within them Faraday's law, Ampere's law, Gauss's law, Lenz's law, and now we can go to a fully relativistic theory with just a little bit of effort. Unfortunately, we've run out of time, but I do hope that you will study this very beautiful subject. Good luck.